Today's lesson will focus on properties of functions, but in context. We're going to take what we know about properties of functions and use those to help us solve problems with contextual situations. For our first example, consider that we have a box. It has a volume of 12 cubic centimeters, but for whatever reason, we want the surface area of the box to be as small as possible. Businesses employ this model because oftentimes they are trying to package as many items as they can into a certain space, so they need the surface area to be a certain size, or maybe they want to cut down on their material costs while still providing the same volume to their customers, so they want to make a smaller shape, either a smaller pop can or a smaller cereal box or something like that. So in this situation, the box has a square base and a fixed volume of 12 cubic centimeters. Let's let the length and the width of the box be x and the height be h. So we can write the volume equation as length times width times height. And since it's square, we have length and width both being x's, which gets us x squared times h, which equals 12, as we stated earlier. So this is something that's given. We know the volume equals 12. We can also express the surface area in terms of x and h as well. So if you remember surface area, it's just really all of the faces added up. So if we take the area of the four lateral faces, we have x times h, length times width, times 4, since there are 4. And then if we look at the bottom and top, well, those are both x times x to give us x squared, and we have 2 of those. So our surface area can be modeled by this equation. When we're looking at functions in context, you will often have to draw from previous information that you know about different formulas in geometry and other areas in order to build your models. Okay, back to our problem. So in our problem, we have 2 equations, one that represents volume and one that represents surface area. We are trying to minimize our surface area. So we're trying to find a minimum. But if we look at our surface area problem here, we have 3 variables, s, x, and h. We cannot graph a function with 3 variables. So if we want to analyze surface area, we can express s in terms of just one other variable, x, if we get rid of this h. How do we do that? Well, think about systems of equations. We can express the surface area as a function of x, meaning we'll have s equal to only an x variable, if we consider the volume equation and the surface area equation as a system of equations. So we have 2 equations that we can combine as a system of equations. If we use substitution to get rid of one of our variables, then we can use the volume equation to rewrite the surface area equation as the function of x. Pause the video and think about how we might do this. Remember, our ultimate goal is to get rid of h. If we want to use substitution, let's rewrite this top equation as h equals. In order to do that, we need to divide both sides by x squared. If we do that, we're left with h equals 12 over x squared, which means we can take and plug that into h in our bottom equation, and therefore we will no longer have any h's. So let's do that. We have 4x times, instead of h, 12 over x squared plus 2x squared equals s. All that's left now is just to simplify. If we want to simplify, we can take 4 times 12 and get 48. We can eliminate one of these x's by taking x into the x squared. We're left with just x, and then we have plus 2x squared. Now we have a surface area equation that we can graph in our graphing calculator. When I graph this in my graphing calculator, I want to focus just on quadrant 1. The other quadrants don't make sense for this type of problem. We obviously aren't going to have negative side links, so we wouldn't use quadrants 2, 3, or 4. So I'm looking in quadrant 1, and because I want to minimize, I want to look for that minimum point, which is right here. I also wanted to be able to understand what this minimum point represents. Well, think about what this is. We have x, which is 2.29, and y, which is 31.45. Y is represented by s of x, which represents the different possibilities for all the surface areas of the box. So I can have many different surface areas, with this point being the minimum at 31.45. Now, this is obviously given that our base was a square and the volume of the box is 12 centimeters cubed. To identify the minimum surface area, we found the lowest function values for y, which was right here. In this case, with the side length of 2.29 centimeters, I can have a minimum surface area of 31.45 centimeters squared. Eventually, when you move on to calculus, you'll learn some other methods to minimize and maximize a function other than graphing. But for now, we are going to just look at these representations graphically to help us to understand this better. Let's look at another example. In this example, we have a trash container. It's in the shape of a right circular cylinder and it has no top. The volume is 22 feet cubed. So what radius, which would be r, will minimize the amount of material needed to make this container? Notice that our surface area equation is equal to pi r squared. This is the circular base. If we were including the top, we would need to multiply this by 2, but we do not have a top. And then the lateral area, this curved area around the middle, is represented by 2 pi rh. So how would we solve this? Pause the video and see if you can solve this on your own. In order to solve this problem, we are missing one equation. What they give us is volume, so we need to construct a volume equation. Our volume, 22, is equal to the base times the height. Our base is pi r squared and our height is h. Once we construct the volume equation, then it's very simple to solve. We can solve it very similar to how we just solved the previous example. So I'm going to isolate my h and get h is equal to 22 over pi r squared. Using systems of equations and substitution, we can take what h equals and substitute that in for h in our surface area equation, since our goal is to minimize our surface area. When we rewrite this equation, we get a surface area of pi r squared plus 2 pi r, and then in place of h, we are substituting 22 over pi r squared. Notice that we only have two variables now, s, which represents our y, and r, which can represent our x when we graph. All we need to do now is simplify this problem a little bit. We can get rid of this r and the squared. We can eliminate our pi's, and then we can multiply the 22's. The 22 and the 2, I should say. So our surface area is going to be equal to pi r squared plus 44, 2 times 22, over just r. And now we can graph this equation. Here I've plugged in my equation into the Desmos.com graphing calculator online, and I have surface area represented by y and the radius represented by x. So I have my pi r squared plus 44 over r, or in this case s. Now notice once again my graph fills multiple quadrants, but I'm really just concerned about the quadrant here on the right because that's the only one that has a relevant domain based on what I want to do. So I'm just going to focus on this area here. And when I focus on that area here, I can see that if I want to minimize my point right here, that is my minimum. Finally, what does this minimum point represent? Well, given a radius of 1.913 centimeters, I believe we said, our surface area will be minimized by having 34.5. And that's actually feet. We used feet. So 1.913 foot radius will give us a surface area of 34.5 feet squared. And that will minimize the surface area of that trash can. And that concludes our lesson on applying properties of functions in context. So remember, when you're walking through the practice problems, you may have to look up some different formulas, geometric formulas that you've used in your past in order to solve these problems.